Welcome to Chapter 6. Chapter 6 is a continuation of molecular orbital theory, guys. Molecular orbital theory, is our best approximation of the truth for a lot about what we care about in inorganic chemistry, organic chemistry. Anytime you're dealing with molecules, you're going to be going to wave functions, right, at its core. A theory based on quantum mechanics very directly, and so that's why we're sticking with MO theory for the rest of the course. So we're now doing a subset of MO theory called Walsh diagrams. And the whole purpose of these diagrams, as you'll see, is to predict the best structures for molecules. And so now, finally, in this chapter, we're going to be able to tie back into VSEPR, right? And we now have an answer. We now will have an answer to VSEPR, okay? Because we'll be able to come up with structures and see, can we solve some of those mysteries, right? Where we just had to throw up our hands. I mean, VSEPR just couldn't get it right for not most, but a good number, right? There's a good number of exceptions where there is not even any after the fact rationalization we could do to explain the structure, the experimentally observed structures for a number of small molecules. All right, so that's the idea here. We're doing structure determination based on MO theory. We know MO theory is based on quantum mechanics, so that's going to be a better predictor than VSEPR. And here's sort of the bummer part is that we don't get the structure, the lowest structure directly. And so one approach, and sort of the most obvious approach to use, is to draw all of the different MO diagrams, compute all of them for all the different possible structures you can think of, right? Okay, is it octahedral? Is it a distorted octahedron, etc., right? Is it planar, a planar hexagon? And then compute the energies and see which one's lowest. That would be a way to figure out the most stable energy configuration, the most stable structure using quantum mechanics and MO theory. What we're going to do, though, is we're going to use what's called Walsh diagrams, and this just makes our life a little bit easier. It allows us to just compute one MO diagram and then tweak it from there to get the other MO diagrams. And so that's all it is. It's just a little bit of a trick, just a problem-solving trick that we're going to learn. Fundamentally, nothing really is changing in this chapter as compared to last chapter. Okay, we're just applying it to different things, i.e. structure. So I want to go a little bit more in detail into the energies in MO diagrams. So far, we've been pretty qualitative. We say things with similar energy and same symmetry mix. That's true. But we're just going to get a little bit more quantitative here. And if you really want to get quantitative, you have to do the calculations, right? You have to evaluate those integrals. You can't just say yes or no, which is what we've been doing so far, in effect, right, when we're thinking about symmetry. But anyway, so we've generally been talking in terms of electron volts. You can convert electron volts to your favorite energy units, but that's what we've been doing so far when we've been talking about atomic orbital energies, molecular orbital energies, and ionization energies. And so just to give you sort of a feel for this, the numbers that are involved, the average bonding interaction is going to give you a stabilization of about 2 electron volts from the lowest atomic orbital that it comes from. The average anti-bonding interaction is going to raise you an energy from the highest atomic orbital that you came from, that the molecular orbitals came from, by about 4 electron volts. This shouldn't surprise us that this number is higher. The magnitude of this number is higher than the magnitude of this number, right? Because we said anti-bonding interactions are always destabilized more than bonding interactions are stabilized. Otherwise, there'd be no incentive to make a bond. And the other point here is that antibonding orbitals are always more antibonding. That's what this just said. Again, that's what it just said. Than similar bonding orbitals are bonding. These numbers will be smaller if the orbitals are more diffuse, i.e. you're going down on the periodic table. Now you can't have as effective overlap between the orbitals because the electron probability, right, is more spread out. And so yes, you'll still have, let's say you have two 2p orbitals, right? And now you go to two 5p orbitals. In those 5p orbitals, yes, you'll still have some electron density near the lobes, the ends of the lobes where there is overlap, but you have a lot of electron density elsewhere that's not contributing to a bond. So that's why, you know, you go down the periodic table, you generally have weaker bonds, or if they're just more core-like. And more core-like is code word for not similar in energy, right? So we saw that, you know, if you have core electrons, well, they're not similar, they're too far away to make bonds. And this point is pretty important and one that we will come back to multiple times, and will be helpful in your homework problems. A molecular orbital always resembles most closely the constituent orbital to which it's closest in energy. So if you're going to draw an electron distribution profile, if you have one atomic orbital that is closer in energy to the MO that you care about, the picture of that MO, the electron probability profile, is going to look more similar to the atomic orbital to which it's closest. And we'll see examples of this. Lastly, if you have a large gap between the LUMO is the lowest unoccupied molecular orbital, and the HOMO, highest occupied molecular orbital, that will give rise to a stable molecule. And we'll see why as we go through this. All right, so that's kind of just a general introduction. Next, we're going to talk about actually looking at the structures of specific molecules, starting with water.